Okay, I think now the recording should work better. So for the last lecture, I think half of it was without sound. Sorry about that. But this one should work fine. So let's start with creating a new project. Let's call it CPP hacking. So we will start by just creating a class for testing. Let's call it CMy class. Okay, and we will create a parent class MyBase. Okay, and on the base class we will of course define a constructor and a virtual destructor. Although for now let's comment it out, we will not use it at first. Then we will add a variable. We don't care for private or public specification much, so we make public everything. Since whether something is public or private effectively only has an effect on what the compiler allows you to access. It does not is not represented in the binary representation of the program later on. Okay, and here we'll add two virtual functions. Function 1, and let's the function just print some text. Oops. We need to include stdio, or was it stdlib? Let's include both, just for good measure. And here we'll just print the name of our class and the name of the function, and then and of course new line. And then the function 2 will do the same. It will just print for starters the second element, and then we'll add one more function which will not be virtual. We call it do something, and it should just call function 2. Okay, and in our derived class we also make it of course public, such that we can create it. Well, right, we should initialize the variable. Base class. Yeah, that's okay. And let's also create a second variable here, which we will initialize with another value. Okay, and then of course we will have the same two functions, just that they will of course have a different class name, since they are doing something different, obviously. So that much to this. And we can of course quickly test whether it behaves as it should. So we include my class, and then we can create an object. Oops. So my class is good. 1, 2. Then we can call do something on it, and as you of course expect, we just print the names of the. So it will just print those two lines. It will not access those lines, since the function overrides those. Just to hammer the point home, we can actually create here a pointer. And call the do something on it, And it will still, of course, only print the 2 lines from the derived class, even though the pointer itself points on a object of the type base class. And as we see, it prints right, we only printed one of them. If we want both lines to be printed, we of course would need to call both functions. Okay. So we see it works as expected, and of course if we would create a new object that needs a value and call again, do something on it, it will then print the other 2 lines, since now we have the right, it was already defined. I can just reuse the same pointer. So as you see, that's the normal behavior that we already have learned during the last lecture, but now what we are interested in would be how these classes actually internally really work. So how could we in some way access those functions if we would not have a C++ compiler. So first what we would, so let's comment this out. Actually what we could do, just to demonstrate it even better, we just comment the whole thing out to create a new C file. So as I mentioned, I think already at some point, when we create a file with the extension only C, then we can only use the normal C inside it. We cannot use any C++ features. The compiler takes the extension into account when deciding which feature set to apply. So we will create a new main function in here. We have commented the other one out. So we genuinely right, and we don't actually want to include that thing, since we cannot include anything that would contain a class into a plain C file. That would not compile. Let's include this and include Windows H for good measure. That should give us everything we need. Okay, so the first thing we have to think about is how our classes, our 2 objects, where do I have them here, my C my base and C my class, would actually look in memory represented just using a struct in C. So as my base, HP. Okay, so what do we already know? We can open this on the side here. So typo. So one thing we know is that the derived my class will of course contain the base class. So we can actually already here define one variable, and here to we just look what we have, and on the first glance we only have here our variable 1. So we put it there, but it's not as simple, because since this class is using virtual functions, it also needs a variable somewhere which would hold which actual class instance this object is. So there is a hidden variable which we don't define by ourselves. It's defined by the compiler, and it has it is basically a table of function pointers. And here, of course, we also have our second variable. Okay. So that's the very first start, so to say. And what we would want to do would be somehow to test whether we can use those structures to actually access the object. So maybe actually we should create here a test function. Let's call it my test1, which will take just a pointer so that we can feed it pretty much anything. and we actually will go back to our main function. We will just invoke the other function from it. So this will make the testing easier. So since we are now in a C++ file, we need to tell the compiler that the function which we are including stems from a C file. So we can do it by writing extend C and then the function definition. We also could use a whole code block and then put more things in here, depending on what we want to do. So let's stay with this nomenclature. So what we now will do is we'll pass our pointer to our test function, and inside this test function, for starters, we'll just try to read the two variables. One should be 1 and the other one should be 2, or let's maybe give it a more unique value, 1, 2, 3 and 4, 5, 6 or something like that. Okay, so the first thing we do is we will of course need now to know which type this is exactly. So since we know that we are passing the my class type, then here inside we can actually cast to this type. So as my class. So we cast our So we cast our C my class to our S my class. So the name is similar, but it's really a completely different object, although it is supposed to look the same. So we will see whether it works. We just try printf. %d and %d one will be the one variable and the other one will be the other variable. Var. As you see, it looks a little bit different when accessing, since we cannot directly access the variables on the base object. We need to go through this helper variable. We could of course just copy everything and paste it here, but we want this to look more how to say it, we want the whole thing to look more have a more direct comparison to the class that we created. So we will not be just copying everything around and make it more convoluted than necessary. Okay, now just let's run the test, and we expect that we have passed the right addresses, and then we should get the right values. And as you see, we do. The order in which we got the return values is correct, but it might look nicer if we actually switch it. So let's do that. And the next thing that we will want to do will be to be able to call one of the functions here from within our C++ file. So accessing variables, of course, nice, but usually when you have classes, then usually you would want to interact with them through the functions they expose and not directly modify the variables. So let's now try to do that. So one thing we need to take into account when doing this is that depending on for which platform we are compiling, the syntax will be well, the semantics will be slightly different. So we use the preprocessor to distinguish the x64 and x86 platforms. Okay, and now what we will just do is we will create function prototypes for those functions which exist here. But we actually need one more thing before we can do that. Just a second, let's see. No, we don't need, actually that should work just fine. We will need the addresses of the functions though. So let's create here a small enum which we will feed with the indices of the functions. So If you would have a destructor, then it would be first. But since we don't have one, we just go with function 1 is 0 and function 2 index will be just 1, but since it's an enum it will be automatically incremented. Okay, so let's write our function. We just call it as a func1 like the other one. Since the function is defined on since both functions are defined already on the base object, then we'll want to pass the base object here as well. And the function takes as the first argument a pointer to the actual object. So here you don't see this argument being passed because the way C works is it abstracts this for us, so the compiler does this automatically. But if we want to manually from C call a C++ function, then we need to first pass the pointer to this object. Yeah, so and then we will need to call the right function. So what we will try to implement here will be a mechanics which will, depending whether we pass this object or this object, always pick the right function 1 and function 2. So it's a bit more convoluted. So first of all, we get from our object the vtable, and from the vtable we get the entry at the index position. The whole thing then needs to be cast to the right type, and the right type would be void asterisk const void asterisk. Okay, and then we can call the function and we pass the first argument. It's already set the object argument to it. Do I have a typo? I have a typo somewhere. I'm missing right here. I need one more bracket somewhere. Alright, this one was too much. That was fine. Almost. Wait. Open, close. No one too much. I need to open. Yep. Okay. Then we can just copy it for the second function. And it's almost identical. We just change the index. And in case you would want to do this in 32-bit, we will need to specify a calling convention. And as we might remember from the before lectures, in 64-bit there's always the same calling convention used, so it's not explicitly necessary to do it. This is why we need to define these two functions independently. Okay, so now what we will try is we'll just try to call both functions. We called it this. Oops. Base, just base. The function doesn't take any arguments. Do we need the references? We need. And function 2. Okay, test 1 was already set, so let's run it. And what we expect now to see is, okay, let's here as also \n. First the two numbers printed, and then those two lines here being printed. And as you see, it worked. So now what we need to do is we will check using the other object. So now we overwrite our pointer with something that just points to the base object, although this will this line would now fail since we don't have the base. Since we don't have the variable 2. So we just comment out for the quick testing and run it again. And we see that now it, as it should, wrote as the called for us the functions from the base object. So what we can do now is we could actually enable our destructor. This necessitate us to add the index for it, so that now we changed it. So let's quickly check whether it still works. The order of the functions should be just the same order in which they have been defined. Yep, works fine. In your class. One thing to remember is that if you change the order in the derived class, this will have no effect, so this will still work. Although here we were testing it with the base object, so just for good measure, let's comment this line out and test it also with the derived object. So as you see, the order is defined by the first time when the function with a given name is defined, and if the order is later changed, this change has no effect. If you would to change the order here, we would actually see that we would then print we'd first call, so normally we want to call function 1 and then function 2, but since we did not updated our index table, when we change the order here, the order change will be applied here as well. So when we think we call function 1, we actually are calling function 2, so that of course would be a bug. This is why when doing such things one would need to maintain the order of the functions and don't change them later on. Also in normal use cases there is not much reason to do such things, so you could save a few bytes of memory trying to create and access objects manually, but usually this is more useful if you would have some library, for example, which exports some class and then you want to manipulate it in some way. So what we can, for example, also do is we can hack the vtable and change the behavior of the class if we want. So one thing we can now do is we could define our own functions, so functions that could be used in place of the functions that have been provided originally. So let's maybe start with that. Right, is const void object. Let's just go with const void for now. Then of course we do the same for our derived. Let's maybe add the s here to the name. Let's write it like this. That looks nicer. Okay. Now, of course, if we would have a more complex inner logic in the function, then we would need to do some more work. But just for an initial demonstration purposes, we don't need to make the functions any more complicated. So what we do now is we'll define our own vtable for the base object. Base function 1 and base function 2, and then the same for the, actually maybe it would look nicer if we put this here and that there. Then for the derived object we take the second one. Okay, so now let's define a new test function that will do something different. Okay, so in our test 2, what we could first try is we could actually create an object for ourselves. Ah, wait, we forgot the destructor. So we need to add a destructor function as well. Comma. Right, yo. Okay, so we have a destructor. So what we'll try here is we'll try to actually create an object in C and then pass it out to C++ and then call it as, and then use it as if it would be a normal class created in C++. So we want to go with the derived one as well. So let's create an object of this type. Per my class is equals malloc size of. Okay, so we allocate it. We can have a check whether that was successful. So if it wasn't successful, then we just return null. What we are missing now would be any sort of constructor invocation. So just for a good measure, we can just mem set everything to 0. That we at least have some defined state. Okay, and now as base table is equal our that one is should be called my class, obviously. My class vtable. Okay. Yeah, and then if we want, we can also assign the other variables manually. Let's go with the reverse. Actually, we don't need the memset since we are overwriting all the variables anyway, so let's get rid of that. Right here, and now we just return our object. There was one thing we haven't done yet. We haven't done the destructor, but we don't really need to make it do anything. Okay. Now, what would be, of course, a reasonable approach to some extent would be to not try to use the delete operator on the class, since we created it with malloc and not with new. So so depending on the actual use case, we might need to put more thinking and consideration into the object creation and destruction. But just to demonstrate the general principle of how those things work, I think it is enough to demonstrate it in a more direct way without thinking of all the special cases that might need to be taken into consideration at some point. So here we can just comment out everything. And then we just need to cast the void pointer to the right type. And now we can actually even it should work to call do something on it. Let's try. Because the function, this do something function, it's defined somewhere, it lives at some position, but since it's not virtual, it just has an address in our program, and that's it. So we can call it, and what this syntax will do is it will pass the pointer as the first argument to it, and then the function internally, knowing that these functions are virtual, will dereference the vtable and then actually invoke our very own functions which also just print, but they print with the with two underscores instead of two double dots, as you see. So there will be a clear difference. So let's run it. Zack. Let's check the result, and as you see, it worked just fine. So are there any questions at this point? No questions? Okay. Good. So let's try the next hacky hack. Let's comment out this again. Let's enable those two lines. So as we have seen for now, we have seen how we can access and call effectively functions on a C++ object just from normal plain C. And we have seen how we could even create a C++ object in C and then use it in C++. So the next thing which we will try to do will be, we will try to manipulate a C++ object. So we will want to change how it behaves, how it works. Right. So we will pass it a pointer to the object which we want to manipulate. The object will be, actually we don't even need necessarily to know the type of the object at this level of abstraction, since we know that the first entry is always the vtable. By the way, vtable just stands for a jump vector table. So we actually don't even need to use these two types. You can just directly access the first member. So let's do that. Right, asterisk. What we what asterisk. Let's write. Oops. PTR. So this way we can write something to the table. So we can override the variable. So what we need here will be a new vtable. At this point, it's of course already the very hacky area, since we will not even consider a method to later deallocate the memory. We just want to manipulate it for now, and if we would want at some later point to properly free everything, then that would be a subject for later. So we know we have 3 entries in the table. Since we have the this factor as well, so 1, 2, 3, and we know that each table entry has the size of a pointer, so size of void asterisk, and open, close, yeah, that's it. We can cast it, and then the first thing what we do is we'll just copy the old table onto the new one. New table, comma, old table. We need to reference that, okay, and we use the same size. And now we can apply our hack. So let's replace function, the first function that was index, this one, with a hacked version. So we need now to create a hacked version of a function, void hacked function 2. And what we can do to simplify it, we can just take, we can just copy from here. We don't need to retype the whole thing. And although we could want the function to operate on the derived object, so maybe let's take the pointer to the my class, and then we can access both objects internally. So printf %e backslash n, that will be the two variables. Oops, it will be the two variables. So object base var1 and object var2. So the function is simple. We can assign the function's address to the new table, and then of course we want to overwrite the address on the table. Now, one thing to note here is that we need to make this copy. We cannot just overwrite the vtable entry directly to which is pointed by the object initially, because this the way C++ implements its derived classes is such that it creates one vtable for every type it has. It does not create like a new instance of the vtable for every object to instantiate, but it just reuses the exact same vtable, which makes sense since there is usually no point in creating different vtables dynamically. So this is why we need to make a copy and cannot just overwrite the existing one. If we would have overwritten the existing one, there would be what we would have done is we would have changed the behavior for all the objects of this type. So even if we would instantiate the object in C and never in C++, I mean, and never modify it in any way, it would still be subject to our modification, which in some scenarios might actually be desirable. So this is this is something to be kept in mind. So yeah, let's try whether it works as expected. So we have our object, but we need of course our test3 function, and we call test3 on our pointer, and then we do something, and we expect the first line printed to be replaced with a function that prints this, and actually we should also add maybe the name so that we know that it's it. So let's run it now. And as you see, instead of the function which should have been called, now our hacked function. Alright, and we have overwrote the function 1, not the function 2. Yeah, small typo there. So let's rerun it, of course, and now we will have the right text. And we could, of course, have done this with both functions. So if we want, we can just copy this function here. We should rename it everywhere. So we can just copy it. Func2. Function 2, and then we could here also overwrite the function number 2. Let's quickly check it. As we see, it works just as expected. So this demonstration, I think, shows quite nicely how this seemingly complex C++ objects are realized by the compiler, and that it's actually quite trivial the way it's implemented. It is just a function, a set of functions, and a function table as a first entry in the object. So just to complete the demonstration, let's actually create a third example where we will modify the behavior of all the objects, not just. So basically what we want to do is we would want to modify the vtable, the original vtable that the compiler created. But this actually is not that simple, because in modern systems the compiler tries to ensure that but through just overwriting memory, an attacker cannot manipulate the code flow in a program, or at least can manipulate it as little as possible. So the vtable will be put into a area of memory which is marked as read-only. So what we will need to do is we will need to first change this protection property. We can for this use the virtual protect function. We pass to it the address we want to change the protection for. Then we pass to it the size in bytes for how many bytes we want to change the protection. And what we also can do is we can so it will, so first of all we of course want to specify right, let's specify what it should be, but what it also does, the function, it returns us the old value, such that we can restore it after we are done with our meddling with that memory region. So let's do that first, and now we will do our hacking here inside. So let's say we only want to change the behavior for function 1, but we want to leave function 2 unchanged. Unchanged. So this should be all. And now so we need, of course, to pass the address here so that we can actually find out the address of the vtable, but we are not changing anything in the process specific in the object specific data. Oh, wait, did I not rename that? Yeah, that should be, of course, test4. So let's add it here. So test4, pass with a p pointer, and now what we'll do is we'll create a new object of this type, and on this new object we will we already used that name 1, 2. We will call the do something function, and the expectation is that it will change that the second line, so that the first line will be changed to our hacked function. So let's run it. And as you see, we have changed the behavior for all the objects of this specific type in our entire application. Okay, so are there any questions? No questions? Okay, so if there are no questions, then we can continue to the next part of the lecture. So let's quickly save the project and close it. So the next thing I would like to show you will be how to use the properties of C++ to help with memory management. So let's create a new project. It's the smart pointers. Let's call it smart pointers. Create. Okay. Oops, not too much. Okay, so as you might remember from our previous earlier lectures, with C and C++, you always need to take care when to deallocate memory if you have allocated some. So let's start with an example. Int asterisk my array is equals new int 100, and once we can do something with it. And once we are done, we need to call delete on our array. So far so good, and in straightforward simple code that also does not appear like a too difficult demand to just remember to deallocate it, but practically there are quite a few cases where this is not that straightforward. So first of all, if we have a function which has some non-trivial complexity, and within that function we would want to return at some point, then so let's do this example. Void my func, then we move our memory to my func, then we just call my func, and let's give it a few arguments, 1, 2, 3, 4, 5, 6. Then here int 1 and int 2, and let's say well, we would do something, and then we could do something else, but in the middle we want to check if arg2, let's say, is less than 200, then we want to return already. Doesn't really matter which special cases we would want to handle, just that what we want to do is we want to return prematurely from the function. And if we would do that, then the memory which we have allocated here would remain allocated for the runtime of our application. So what we need to do, of course, in this case, is we need to first manually delete it before we can return. And if you have a more complex function and create a few dozen or half a dozen of variables which contain pointers and which all needs to be deleted, at some point your program will be just full of things like that. 1, 2, 3, and this, of course, well, it's not readable, it's easy to forget. If you introduce later yet another variable, then you need to keep in mind that you need to add it everywhere where you might want to return. So it's not the most user-friendly approach. And another thing to consider, of course, is that if your function would to throw an exception at some point, so let's say here somewhere in the middle we install a bug, int x is equals 0 and int y is equals 1 and int z is equals 1 divided through x. So let's say if we divide by 0 somewhere, actually we don't need that. So this would throw an exception, and this means that you would allocate memory, and at this position you would directly bail out, and you would have no opportunity to deallocate the memory. So this is also not satisfactory. If we ignore the case of an exception, then of course through a smart usage of C functions one can somewhat make this more elegant. So for example, we could here have a finish label and then just say go to finish, which is as good as saying just return, but this has other limitations, as we have seen during one of the earlier lectures. When using gotos, you need to take into account the lifetime of your variables. So well, the compiler checks this for you. So if the effect is basically that if you would have some variables defined somewhere in between, somewhere here, even if it's just an int test1, okay, with an int it might work, but but the point is, if the variables are already at complaints even for this one, so you see here it says that it goes over test1. So that the thing is that the code must be consistent from from when you jump to a label and to the label. So here, if we would have some more complex code, so if this would be a more complex object, or even if it's a normal object, if the compiler at this point needs to put something, allocate some memory on the stack, then it would always need here, when it is done with this memory, deallocate this memory from the stack. So the issue even happens for built-in types. But if we jump to this code from here, then we have not added this memory to the stack in the first place, and the result then would be here that we would remove more memory from the stack that was allocated, and that means stack corruption, the application crashes. So this goto method is highly limited, because basically you need to put all your variable definitions at the beginning of your function, or at least before the first use of a goto instruction. So this kind of is not really the best way of doing things. Another way how you can do is you make a loop that basically just makes one loop and doesn't do anything. So you make a do while loop, and then at any point in the loop you can, if I don't know, 1 is less 200, you can just say break, and this actually works out nice. So we can define variables later, you can define variables before. You will be always able to break out of this loop, and then since you break out of it, you directly end up at your finish. one of course thing to remember is that you would still need to define all the variables that needs cleaning up outside, but you don't need to allocate memory for them. So you, here we could replace all the direct delete instructions with ones which just check whether the variable actually exists. Plus, it's worth mentioning that actually calling delete on a null pointer is valid. It just does not do anything then. But of course, if you would have some more complex objects which need a different handling than just being deleted, for example, handles that needs to be closed, like file handles, then you would need to check whether they are valid or not. And then you could, within your code here, within your single run loop, basically, you can create the handles as long as the variables are set here outside. So as you see, there are ways how this can be handled just using the means available just in plain C, but C++ gives us a much more powerful tool to our disposal, namely the fact that when an object gets out of scope, the compiler will automatically invoke the destructor for it. So let's create a new function, my test, and try to use this for something useful. Okay. We also maybe want to pass some arguments to this. So my But of course, what we now will need will be some object which will be able to go out of scope. So let's create a class for that. Let's call it scoped pointer. It just takes a random pointer. Actually, we could improve this using a template. Okay, so we can create an object and just assign a pointer to it. So let's quickly do that. Scope pointer from type int my array access like new int 100. Okay. So at this point, nothing too exciting happened yet. We just created a pointer which holds a value. But the interesting thing is now that we will just add a destructor to it, and the destructor will. So there is one small limitation. Technically, you are supposed to call the destructor with this empty brackets if you are destroying an array, and just a delete like this if you don't. If you just have a single element, but as far as I have seen under Windows, both work without problems. So it's not actually correct to just use delete without those if you have allocated an array, but I have never seen this fail in any way. So let's do this here such that our pointer will be able to work with everything, and later I can show you how this can be improved. Okay, so we have here our pointer, and we of course need to specify a type. And what we'll now of course want somehow will be the ability to access this array. So as you might remember, we can create an operator that will be team reference oops and false. Okay, add false. And what we also might want to do is we might want to access a more complex object. So let's include string and create here another pointer. This is a string. Nice. So we create here now a pointer to a string. So what we would now again want would be somehow to access the things that on a string could be normally accessed. And while one could of course just say that this thing will not be private, and then you can just access it. That's not elegant. So what we do is we can actually implement another operator. What was it? T asterisk. Oops. And now with this operator we can directly access all the string members that are on our SED string class from our pointer object. So our smart pointer, our scoped pointer, behaves just like a normal pointer would. If we would have just a normal pointer, we would just use the arrow operator and then could access all the elements as well. So let's go with assign something. Okay. And this is already enough for our smart pointer, for our scope pointer. So smart pointer is a general description for complex pointer objects which can do more things internally. And they are usually much more sophisticated than this scoped pointer object here. So this one just keeps track of one object. It is not supposed to be assigned a new value later on, although as you see currently there is nothing to prevent that from happening. So one might want to define a maybe a copy constructor which would be defined as private so that it cannot be called, and the assignment operator in the same way, depending on what protections you want in your code. But what basically happens here is that if we now do something like we had before in our test case, then just return. Whenever we return from a code block, the compiler will automatically invoke the destructor, and the destructor will deallocate the memory for us. So we can maybe put a breakpoint here and then step through the code quickly. Okay, so want to step in. Zack. We create one pointer, we create the second one, and now here if we return, you see here we have a call to our scoped pointer which takes the string, and we have another call to the scoped pointer which has the int. So we will invoke both destructors when this return happens. Of course, internally it generates quite some code, so it's not always so the approach with the goto or with the break here would end up with less code, assuming of course you have like multiple returns in multiple places. But for once this can be optimized further by the compiler, so it is so wasteful only in the debug build. In the release build it should reduce the usage of redundant code blocks, so just jump to a code block at the end and do the cleanup from there. And what of course can be done is you don't need to have a delete in your destructor, but you can in fact have any sort of resource freeing operation. So if you would have, for example, opened a file somewhere, then here you could have a close handle close or fclose depending on which API you are using. So it is quite a flexible approach. More advanced smart pointers exist, and they are in fact part of the standard template library, and they should be used nowadays whenever possible, since they help you not to need to care that much for the memory management yourself. So as you see in this case, you just create the object and then the object will be deleted once it's no longer needed. There are some limitations, of course, with smart pointers in C in comparison to fully memory managed languages like C# or, for example, Java, namely that you don't have any sort of garbage collection in C++ at all. So when you have objects which utilize smart pointers, you must avoid to making two objects point to each other mutually, because if they are pointing to each other mutually, then the smart pointer will never get to a zero reference count and will never be freed, even if those two objects as a group would no longer be referred by any part of your application. In memory managed languages like C#, there is a thing called garbage collection, where a mechanics provided by the framework will check the whole application periodically for objects which can no longer be referenced by the actively running part of your application. And even if there are some circular references within them, this will be properly identified as no longer needed memory and freed. In C++, such things don't work this way. So, as said, you need to take care not to create any mutual references. And one way of doing this is to use so-called weak pointers. So first we will improve our scope pointer a bit, and the next thing we will do is we will take a look on the pointers as are provided by the standard template library and what can be done with them. So as I mentioned earlier, today one problem with our class here is that always use delete and not necessarily the right delete brackets. So one way we can remedy this is we can provide an optional parameter for the constructor which will allow us to specify a custom delete function. So void asterisk deleter void asterisk. So we will of course by default assign it to be null. So if it is not specified, then it is just null, and then it will use the normal delete. But if it is not null, then it will be used. So if deleter, then deleter else delete. One moment, please. Right, so now what we need to do is here, where we have the constructor, we need to provide the right deleter. So how was that? Delete. Right here. Done. Okay, so one of the nice things about the more modern C++ variants is that you can actually define functions directly within other functions like this. So this is quite nice. So now, when the destructor for my array1 is called, it will see that the deleter was specified, and then it will use the right delete function instead of using the generic delete instruction. So this way we could even reuse our pointer to work with malloc allocated memory just by providing then 3. So actually we can demonstrate that, since 3 actually should have already the right syntax for that. Yeah, it needs to be casted. Yep. So this way we can have a large flexibility with our smart pointer. This simple sort of smart pointer is of course very easy to program oneself. If one would want to have more complex functionality, like create a shared pointer, so a pointer of which you can create copies, and then which will reference count, so it will count how many copies of itself exist, and then when the last and then issue the delete only once the last copy gets deleted. But since this is a bit more convoluted, we will not write our own smart pointer just yet. We will just instead use the smart pointers as are provided by the standard template library for demonstration. Okay, let's call it let's call this project STL pointers. And now we need to include the right include. Which one was that? I think it was just memory. Okay. Asterisk. What's that one? Make shared. So the idea with the way that they designed the library is that you are supposed not to use the new and delete and create a row pointer and then pass it to your a special shared pointer, but use this make shared and then have to specify the type. Although this of course just creates you a single element. So yeah, if you would want to create a pointer from, so this is the recommended way of creating pointers from in the STL library by using this make shared, or if you create a unique pointer, make unique. So the pointer which we have created earlier, the one the scope pointer, would be a unique pointer. And so this unique pointer has more or less the same functionality. Sorry, that was unique right here. So this has the same functionality as our scope pointer, and there when implementing this ensure that you cannot easily copy it or do something that you shouldn't. With the shared pointer, you can make as many copies as you want, and once the last copy gets out of scope, then it will be freed. And what you of course can do if you want to assign some existing pointer to one of those. So let's demonstrate that really quickly as well. So int asterisk let's assign this to a unique pointer. Let's have wir 3. So this would normally complain, as you see, but what you can do is you can use the explicit constructor, and then it will accept it as well. So you can create your own object somewhere else and then assign it to the unique pointer. One thing to keep in mind or to notice is that here in the prescribed way of using these pointers, apparently there is no direct means how you could create an array. And the reason for that is that they don't want you to use an array, because if you are using an array you can always specify a wrong index, and then your code will do something unexpected or crash something or cause problems in other ways. So this is why the STL library comes with a huge amount of different container objects, like a vector, which basically is just an array. So this is what we did here to create like our own pointer and then try to assign it here to our unique pointer is actually not recommended if you would want to do it properly. What we would do is we would create a std shared pointer from a std vector from an integer, and then we would create this using the make shared function. So this way we have a smart wait, it's complaining. Why is it complaining? I forgot to press the name. Of course, the name is also important. So what we now get is a smart pointer which points. So the smart pointer is allocated on the stack within the main function, and it points to a vector object which is allocated on the heap. And the nice thing about the vector object is that it automatically manages its own memory. So as you might remember from the string classes, which we have taken a look at in the last lecture, when using just normal C strings, which basically are just arrays, it's not super convenient because you need to know how big your string will be at most, or you need to allocate much more memory than you will ever need it. So it's not great. And if you just allocate the right amount of memory, then each time you want to add something to the string, you would need to recreate the string, reallocate memory, and do all of that manually, which is not nice. This is why you have these string classes which abstract this away, such that you just append text to the string and the class internally decides whether it needs to grow its buffer or not. And the vector basically is the same thing, just for arbitrarily typed objects. So it's like a smart array, one could say. It manages its own size. If you try to access an invalid index, it will throw you an exception instead of doing something nonsensical. This is one important thing to keep in mind about how C++ and C works. While other more more high-level languages would validate things and just for exceptions if your code tries to do something invalid, C is just perfectly fine in doing something that makes absolutely no sense, as long as it's a valid opcode, basically. So using proper container objects which add those checks explicitly is very much recommended. And this vector class, for example, will always ensure that if you provide an index, that the index will be valid, or it will throw an exception here and there. And this way, what we effectively get here is something that we can use just the same way as we would use a normal C array, but now it's not completely safe, but at least much safer. So the memory is managed in the sense that it will be deallocated when it can be. It ensures that it will not be deallocated beforehand. So this is also a bug that people like to do. It is that you have some objects, then you pass these objects around, and at some point you delete those objects, and some other part of your program which got one of those objects passed to in the past was not notified and tries to use it, and the object is no longer valid and the whole application crashes. Using a smart pointer here avoids this. So the object will remain in memory as long as any of the shared pointers that refer to it is still somewhere in the scope of something. Of course, this can lead to memory not being deallocated when you want it, but it's better this way than to have a pointer to invalid memory. So the worst case is, of course, a pointer to an invalid memory. A memory leak is not that much of a worst case, and also since you are using a smart pointer, unless you have some circular references, then you should not have memory leaks which are like permanent. So you can have a situation where temporarily your application will consume more memory than expected, but as soon as some other cleanup procedures that you have in place have been executed, the memory that was kind of in one place forgotten but still stuck in another place will then be cleaned up. So unlike a real memory leak where if you yeah, dispose of the last reference without freeing the memory, you will basically never free the memory until your whole application terminates. So that much about that. So let's maybe test how nice this works. So first of all, with such a pointer, we can just add things to our array. Or of course, if we want to be more efficient about it, we can either use resize or reserve on the vector. So reserve means it will increase the size of the internal buffer to the given size, or just to the size. And if you use resize, then it will not just increase the size of the buffer, but also set an internal size variable to the size that you have specified. So if you just reserve a certain size and then query the size, then it will still say it's 0. It will still say it's empty. If you, however, use the resize function, then it will say it has the size to which you have resized it, and the elements there will be able to be accessed. So let's go with resize. And you can specify a new size, and as you see, the function is overloaded. So there are two versions of resize, one that takes just a new size and one that takes the new size and then a value to which to initialize not yet existing elements. So let's go with that. So let's say we want 100 elements and initialize all of them with 0. And now, like with a normal C array, we can just for int e, sorry, we should use size t. 0, I smaller 100, I plus plus. I forgot a semicolon here. Zack, and now we can just ideally use the add function e. Oops, zack, to access the buffer at this position. And the add function returns you, as you have seen here in the IntelliSense, a reference. So we can use add is equals, let's say I, not 1. So now if we run the code, it will fill our buffer with values 0 to 100. And in principle, we should also be able to not just need the add, but we should be able to also use the square brackets operators, but it kind of doesn't seem to like that. We might not have the right version, of the language set, because I think this was added later. Properties, rightio, that needs to be newer. Let's go with the newest. Zack. Now it should be fine. Let's see if it compiles. No, it does not. Okay, so let's just stick with this version. It would be nice if they would implement the square brackets operators such that you can use it transparently. But well, if we want necessarily to use them, what we can of course do is we can just reference the pointer that it points to, and voila, almost as pretty as the as the normal C array. So let's run it. And I did not put a breakpoint. Let's put a breakpoint. Okay, now we should be able to inspect our element, and as we see, it contains all the elements. And now if we intentionally introduce a mistake, so let's say it's smaller or equal, so that we try to access one more than the amount of elements in our array, and this should throw an exception or an aside here. As you see that there was an attempt made to access an invalid address. So the exact error is a vector subscript out of range. And actually we could click on ignore, and it didn't crash. Oh, it crashed, it just needed some time. So these asset windows that pop up in the debug build, you have the option to actually ignore them. Because the way they are implemented, we can quickly take a look on this again, is that this is an explicit check. Somewhere Okay, we won't find it easy the place. So the STL library is quite convoluted. But what you can do is you can manually use the asset macro. Did not defined. That should be defined. Do I need to include something? Maybe I need to include Windows H. I would assume that is in Windows H. Let's quickly check. No, that. It should not need any extra includes. Why is that not working? Well, that will be something about the project configuration, but we have the Windows 8, so I would expect it to always be included. We might need to include the MFC for that. Okay, let's ignore that. For now. So in the Qt library you have the Q asset, which but we don't have the library here right now, which works in a similar way. But usually on Windows you could have used the normal asset, but for some reason this is not. This is missing a header somewhere. It's possible that this is part of the MFC library. Let's quickly. Wait. I think now it works. Okay, so at some point they changed it to underscore asset. So basically you have a template, and if you pass an expression which is true, let's say 1, then it will just run over it just fine. So let's quickly try it. So it will not complain. But if you pass an expression that evaluates to 0, I mean now I'm just writing it, but you could have a whole equation there or some condition. And if it gets 0, then it throws a window like this. And the option is 1 is to ignore, and if it can be continued, then it just continues, as in our case here, because we just said it's 0, but there is nothing that would fail later on. You can use abbrechen, which just terminates the program, or you can use repeat to get to the breakpoint where this assertion happens. So then the compiler points you to where this happened. Okay, so that much to this. And one more thing that we should take a look on will be weak pointers. So, but actually we should probably somehow better demonstrate how these pointers work. So let's create some test object class see my object. Oops. Public see my object, and we add a destructor to it as well. And we just want to see when the destructor will be called. So let's comment this out for now, since we don't need it. And we will create a pointer to our object. And then we will somewhere here, for example, assign it something else. Then the first one we can assign. Can we will it complain? It doesn't complain. Fine. Or maybe. Oh, is it complaining? That should. Sorry, I should have used shared pointer. That's the whole point. You cannot make copies of unique pointers. Copying and pasting without looking what one is copying is maybe not the best approach. So what we are basically doing here is we have our pointer, we are assigning it to this one, and then we are clearing it from the other one, so it stays in this scope, and once we exit the scope, it will call the destructor. So we add a breakpoint here and a breakpoint there. So now when we run it, we should enter this breakpoint before we enter that breakpoint, since the first pointer dereferences, so the reference count goes down to 1. And then, as you see here, we have called it from somewhere here. From this, basically, from below this line, we have here our call to the destructor of this pointer object, and this pointer object checks the actual object which it is pointing to, whether it is the last one pointing to, and then it destructs it. So what we can do here, for example, we can should give us somewhere the reference count, use count. So we get the use count from this, and then so we basically are getting the use count from the second pointer twice, once before we have cleared the first pointer and once after, and the first use count will say 2 and the second one will say 1. And of course, as soon as the use count hits 0, then the original element is being destroyed. So as we see here, use count 2, use count 1, I forgot the new line, but that works as expected. And the nice thing is that you can use the smart pointers really everywhere instead of normal pointers. The only limitation, of course, is that if you have some function which expects a normal pointer, then you need to pass a normal pointer to it. But as you can see here, you can actually get, was it get? Yeah, just use the get function to get the, is that supported? To get the address. Let's quickly see. So in the %p should work to print a pointer, but I'm not sure whether the normal printf supports that. Yeah, it supports it, so we get here the memory address of the object. We don't need to query it again. So you can use this get, and then you can pass your object to a function which would expect the object of this type, which is not a smart pointer. Then of course you need to you need to, of course, to know how this function will then, what it will do with this object. So if it will internally do something, and then once the function returns, it no longer needs the object, then you're on the safe side. If the function would internally make a copy of the object, then you would need to find some additional way to track the lifetime of that object. So that might be, of course, not ideal, but usually with most simple API functions, if they take an object, they usually will not take ownership or make a copy of it. So for the most cases, it should be good to use this get method, but of course you need to be careful enough when using it to ensure that you will not somehow give out an object that will then at some point be referenced once all your smart pointers stopped existing. That's generally the whole thing about C. There is a lot of things to think about and take care of manually. Okay, so one more thing which we will want to do now is we want to try this weak pointer thingy. So let's define one here. Std weak pointer type my pointer null is equals that should work. So as you see, you can actually assign it this way, but now if you run the code, it will still have here only a reference count of 2, so the reference count will not change. That's the whole thing of this weak pointers, that the count stays the same. You see the count is still 2, But what we can do is we can create some third one from our weak point. Does it look? I think it's log. Yeah. So we use the function log on the weak pointer to create an object, to create a not weak pointer, to create a strong pointer, which then will increase the reference count. And the idea basically is that if you would have objects which somehow need to refer to each other, but you need to avoid to create a circular dependency, then what you can do is you can make only one object refer to the other, and the other using a weak pointer referring back to the first one. Then if the first object goes out of scope, the second object will go out of scope as well, and the weak pointer will not hinder this. While wherever you need to access the object, you can create a temporary strong pointer. What you need to do is actually you need to check whether that was successful, because it might not, since assuming that you might have a multi-threaded application, so a program where multiple lines of execution are executed at the same time, you might find yourself in a situation where you have a weak pointer, and in another thread the actual strong pointer, the last strong pointer gets out of scope, and then the object is destroyed. Then you have still your weak pointer, but the original object does no longer exist. And then if you would do this log on this object, then the returned value will be null. You will not get a working pointer. So we can write here if this worked. Oops. Got pointer 3, and then we will repeat the whole thing here, and here we want to fail because since we have here dereferenced this pointer, that pointer is a weak one, and the ones in this scope go out of scope, then here the weak pointer should not be able to create for us a reference anymore. So let's run it quickly. I think we need to remove a breakpoint. Yeah, this one we don't need. So as you see, counter is 2, then got the pointer. I forgot to add a new line again. Here as well. So we have here got pointer 3. Use count now is increased to 3. The object is of course still the same. Then here we are dereferencing the outer pointer, so the use count after this now falls back to 2, and after we closed this brackets, the use count goes to 0 and the object is deleted. And when we try to access it, what we end up is we don't get the pointer. So when using weak pointers, it's important to always check whether the operation of obtaining the pointer was successful. And the important thing here is that those functions are provided by the framework, so they are quite reliable. So if you use the STL library the way it is intended to, and then you will in fact be able to avoid a lot of problems which normally arise when using C or C++. Are there any questions about pointers at this point? No questions? Okay. Good. So then, since we started with the STL, then let's just continue with it. The standard template library was introduced after the MFC from Microsoft. So Microsoft, which had compilers since many decades, And at the very beginning, you kind of just had a compiler and just basic C runtime without any larger libraries. They have introduced this Microsoft founded class library to make the life easier for developers. But since the world kind of realized that those things, such classes, such general templates are useful, people started to work on the STL library, which then became part of the C++ standard. So since a couple decades, you don't get a C++ compiler without STL at all. And while at the beginning the standard template library was quite limited in what it could do, so it was mostly just limited to container types like the shown vector and string, which we already had earlier, and at some later point they added smart pointers. But for the most part it was really just a very abstract, let's say, collection of helper classes. With the later extensions, which, well, it's already not that that new, with the C11 standard, so from 2011, so that's already more than 10 years ago. They have introduced quite a few additional objects which are more, how to say it, so the first part, so the old STL, it had container classes and things that allowed you to work with your code, work with data within your program. It did not contain anything that interacted with the operating system or the outside world, except for just printing and reading from the standard console. With C11, they introduced such objects like threads, which heavily interact with the operating system and abstract those things. So that now, when you are writing an application, so when you were writing an application back then, then you would need to decide whether you want to write it for Windows or for Linux, because the way you would create a new thread would be operating system specific. You could find back then even libraries that, for example, provided a Linux-like API wrapping around a Windows API, so that you could use something that was written for Linux and compile it on Windows. But as said, with the C11 standard, they have introduced some of those most important things into the STL library, like threads, and also some other useful things which we will take a look on in a second. But first, let's create a new project for that and take a look on these new useful STL objects. And as I said, with those you can write a large portion of your application in a way which is now completely platform independent. So you can just use the thread object and other objects to interact with the operating system, and it is abstracted away such that it will work on any operating system. Of course, you need to take into account, for example, the path format, so that on Windows you have the backslash, on Linux you have just the normal slash and other details. But if you would, for example, write an application where the user provides a path as an argument, then internally you could create threads, read files, etc., without the need to write code for different platforms individually. With the new capabilities of the STL library, you can, to a large extent, just use it for all those operating system specific operations. Of course, it's limited to like the most standard things, so very specialized functionality that only individual operating systems and others not may provide, and that you don't get there. But the main things like just started thread, killer thread, etc., those things are available. So here we have a new project. Let's include Windows 8 just for good measure, and we include memory is nice to have, since we probably want to use some smart pointers. And then we want to demonstrate a thread. Okay, so stl the thread. What does this take? T1. and what it wants will be a function that it will be able to then execute. So let's create. Actually, we could probably also just use write a inline function. What does it start? No, does it start automatically? I think it starts automatically when you start it. So here we want to make a loop that will wait for apps. Okay, sleep is a Windows API. I'm not sure if there is any adequate STL replacement for that, but let's just use it. So this will wait for 10 seconds and then terminate. Let's then create another loop within our thread, which will do the same. And that let's both of the threads print something in the console. So print f. And here we print hello from main thread. Oops. Hello from main thread. Okay, let's run it. And as you see, they are both running and doing their thing. And the order is somewhat random, so it really just depends on pretty much what all the other things on the. I think it doesn't. I think the thread does not like the thread doesn't like getting out of scope while it's still running. That's not a good thing. So here what it does is it throws you an error, and then it kind of just kills itself. But of course, killing a thread is quite a bad thing, because then if the thread had some memory allocated on the heap, then it will not be freed, etc. The only thing that will be deallocated, in fact, will be the stack. So there is the join function that you can use, which will just make the thread, so the main thread. So once the main thread arrives here, it will wait for the thread 1 here to terminate. And actually, this case, this crash rate which we have seen here, is already a nice example of a race condition, because if the thread would happen to terminate first, then we wouldn't get an error. So whether it crashes or not would be pretty much up to random chance. But now with this join instruction, we can ensure that this always works correctly. Okay, and what else? So if you would want to do something more specific with this thread, you can use always the native handle function. It returns you the platform-specific handle to this thread. So we could use some Windows function to do something with this thread if we would wanted to. But if we just want to run something asynchronously, so run something in another thread, this part of the functionality is already good enough. In fact, the thread, as far as I remember, is quite a powerful thing, because the way it's implemented, it allows you to pass arguments to the thread in a very easy way. 1 1 1 2 2 2, like this. And for example, with the Windows way of thread handling, so here, voila, our arguments were just passed to the new thread just fine. And with the Windows way of creating threads, for example, you can only pass exactly one argument. So if you want to actually pass more than one argument, what you need to do is you need to create an object with all the arguments, assign the values, then pass the object to the thread, and then the thread internally can then work with it. And while of course the effective implementation here is more or less pretty much the exact same thing, it's abstracted away such that we can just pass the arguments that will go into the thread, into the thread's main function, so to say, just directly as arguments into the constructor of our thread object. And if we look here further out into the implementation, or can't we? We don't. Okay, we cannot do that. That's good. We can go up to here, but we cannot go further up. The files are not available publicly, apparently. Maybe they are with if one logs in somewhere. But let's not do that. The important thing to know is that just while of course the library cannot change the way the individual operating systems are implemented, what it can do is it can provide just an abstraction which makes it much easier for the user itself to work with it. And it is quite convenient, in fact, to be able to pass arguments directly to within your thread instead of having to wrap them into some object separately. Okay, what else would be worth mentioning? Another thing we would probably want to take a look on is, of course, if you have threads. So let's maybe create a few more. T2. How would one access resources from those threads? So if you have such a thread, they run completely asynchronously, and on modern hardware which has multiple CPU cores, they really physically run completely independent from each other. On like super old computers which only had like not just one CPU but actually just one core in one CPU and no hyperthreading, no nothing, the threads basically had to be laid out, just cut in time slices and then laid out one after the other. So there was no true parallelity, but given that that every thread could be interrupted at any point, you could still not make any assumptions about the order of execution. And with modern hardware, which is heavily multi-core heavy, you cannot in any way make any assumptions about the order of execution even more. so what you need is you need some means to enforce some order of execution, and you can do that using a mutex. And again, such a mutex at its core, it will require either hardware support or at least support from the operating system. And then an important thing to keep in mind here is that if you only would have hardware support for a mutex, it would work, but in case of contention, it would be not efficient. It would create a lot of CPU load, which would not be which would not be desirable. So usually all reasonable mutex implementations require support from the operating system, and therefore in the older versions of STL they also were not included. So if you needed multi-threading and mutexes, then you needed to start write platform specific code. But again, with C11 this changed, and you can use this mutex object to enforce synchronization. So what we could maybe do here would be to make some demonstration of this. Let's get rid of the sleeps here because they make everything slow, and let's add some variable which we will want to manipulate. With an int. Let's say that every thread will what will it do? Int my copy is equals this. Let's think. We could just increment it in one counter and decrement it in the other thread, but that would probably work out in the end. We need something that in some way is requires multiple computational steps. So just if we would make like here that the one thread just counts plus plus and the other thread just counts minus minus, I think this would actually work out because unless some caching comes in the way. Let's just try it. I think it would work out because the operation of just incrementing or decrementing a memory region is just one instruction. So the my expectation here would be that it will not create a failure condition that we will see. But let's quickly test it. So once all threads run, the number in G should be 0, and as you see, it is 0. but in the meantime, as you see, it's sometimes 1, it's actually never hitting 0, because one thread got somehow a head start on the whole thing. And as you also see, is the actual threads needed quite a long time to initialize. So the hello from the main thread was executed many times before the other threads actually started. In our previous case where we had the sleep, that one was dominant, so the timing behavior was different. Okay, so as I said, we need some more complex example. Let's do it maybe like this. Let's multiply it by 2. So then let's add 2, and then let's divide it by 2. And the other one will do the same thing, just with minus. And I think, let's see. Yeah, I think that might mess it up already. I mean, it's a pretty simple operation, but at least it needs a couple of those. Okay, that still worked. We could get rid of the printfs to make it faster. It still works. How do we manufacture? So the idea basically is that we don't know the order in which the things are executed. So what we want somehow is just a means to... We just want some means to generate an invalid value on purpose. Let's see. But, maybe we can at least see an inconsistent value in the meantime from the printfs. It still works. It's not always easy to break something if one wants to break it on purpose. Okay, I have an idea. Let's start with a defined value. Let's start with value, let's say 10. And now what we want to do is we want to multiply it by I. Oops, multiply it by I plus I, then minus I, and then divide by I. And if the other one comes somewhere in between with a division and multiplication of the first one, that should break. Let's go do it like 1,000 times. That should break it. So we expect that, so ideally the result should be again 10, but if we manage to break it, the result will not be 10. Okay, we cannot divide by 0, so let's just start this by 1. That was not well thought through. No, it still worked. Damn it, how do I break that? Okay, we can actually make maybe just a more real life test case. It's not that illustrative, but it will definitely be it will definitely fail. Std vector. Oops. The thing is, we probably just have too simple of operations for this to really nicely fail. So the idea what we want to do is here append pushback was it pushback I. So each of each of our functions just wants to add its own numbers to the array, but it's using the same object, and it doesn't use any synchronization. And my expectation now is that the thing will actually hard crash somewhere before it's done, because the internal state of the vector will just become invalid at some point, because it's being written from two different threads at the same time. So it's not pretty, but it should. Damn it! This worked out. It still worked. this is not, it is not ideal if I cannot demonstrate it. So if you have really complex operations where now okay, so it just wasn't so it just was not enough instructions. The delays apparently worked up nicely, but when we give it 10,000 tries, then it just crashes randomly, and it crashes from either of those threads. Where do we actually have this? Our code starts. Nope. Yes, here. From this array, and it will really crash more or less randomly. And now actually it crashed at just I10, so I don't know why it worked before. Maybe we're just very lucky with the first run, where I just had set it to 1,000 go-throughs. Or maybe actually the first thread, that's possible. The first thread was already done executing, because I have removed the sleep, before the second thread actually even started. So actually the access was kind of serialized because this thread start took so long. So okay, so now we managed to demonstrate that we should not access the same object from multiple threads at the same time without synchronization. Now, how do we fix it? Well, we fix it using this mutex object. And this mutex object allows us to acquire access. So we just, before we access some resource, we use lock, and we use unlock when we are done, and then we do the same thing at the other function. And the idea is that even if at the exact same moment two threads both say I want to lock that mutex, the operating system or the CPU hardware, depending on which mutex implementation is used, the most common are actually mixed implementation, but that's details, will ensure that only one of them will actually manage to get the lock, and the other one will be suspended and will then wait for as long as it has until the other one says unlock, and only once it does that, then the other one, or an arbitrary other amount of other ones, will be able to obtain the lock. So it's exclusive in this way, and for example in Qt, which is a bit more convoluted, or maybe I should say complicated, than the STL, there you have mutexes where you can also specify whether you want to obtain read or write access. So if you would have a variable and you know that you can an arbitrary amount of threads can read from it at the same time, then you can optimize your synchronization by using such a read-write lock, because then as long as no thread requests a write lock, then an arbitrary amount of parallel reads would be allowed. So, but this I'm not sure. I don't think that Qt has that STL has this read-write lock, but I can actually could quickly check that. STL. I don't. No, they don't. You can kind of try to create your own, or maybe. Okay, it seems actually you can do that. So the STL will in fact also support. Let's quickly try that out. Unique lock. That's actually quite nice thing. It should work. Which version do we have enabled here? 14 reicht nicht. Gehen wir mit den neuesten. Let's get the newest version. That one should support this. Okay. That works slightly differently. that let's ignore that for now. So that there is a way how you can create read and write logs in STL, but it's a bit more convoluted. So in Qt it's much easier. And for now, to keep things simple, let's just stick with the normal mutex. And also for like the main sort of things that you might want to do with C and C++, just a normal mutex is good enough. You don't need to probably to optimize things so far as to have a distinction whether you have a read or a write access. And if you need, then you can just read up on the documentation for those special cases. It's just good to that you know that those methods exist and you can implement them using STL, even though it's a bit more convoluted. Are there any questions at this point? No questions? Okay. So I think since we only have like I think 3 more lectures left, today is a good day to give you the final project that you will have to finish for your for your evaluation. So as you might remember from last lecture, C++ has all these different operators which allow you to create own objects which kind of behave like other types. And a very fun thing to do would be to create an own object which can impersonate other types. So let's start an empty project for that. Which one did we close? This one is not closed yet. So we create a new project. How to call that? So such types which can represent other types are usually called variants, and they are quite useful because in various scenarios you might find yourself, you might need to pass something of an kind of arbitrary type, but you of course would not necessarily want to use a void pointer because that's just asking for trouble. So what you would want to use is such a variant object. So such a variant object would internally contain a buffer which would contain the data for the object, and then it would implement different constructors such that you can cast from any type that you support to your individual your particular variant, and then it would contain either operators that would allow you to then use this variant directly as a object of a different type, or what is more common, it would contain functions that would then return you a value of a given type. And variants, well, simple variants, they only hold single values, so a number, a string, a floating point number, or some other more complex data types if needed by the particular application. But there are also so to say complex variant types which can also hold arrays or maps. So a map is kind of like an array, but instead of using indices, you use names to access the elements within it. There in fact is a STL object of the type map. Maybe I should demonstrate it quickly, which does this thing. std map, let's say std string int my nums, and then std thing, and then you can just use your square bracket operator, write a string, and then assign to it a value 1, 2 is 2. Oops. 3, etc. And then you can of course access the values the same way. And internally it will just give you then a reference to the element. So you can also override. So you can override the value as well with something if you would want to. And one more thing that maybe is good to know about STL container objects, but we will take a more in-depth look on more STL things in the next lecture, is how to iterate through things. So with the vector map, I think we have seen already here somewhere, yeah, that you can just access it with the @ or with the square bracket operator with the vector like a normal array. But how would you iterate through an array which contains strings? And in fact, in the STL library, the general method of iterating through any sort of container uses so-called iterators. So we use the auto keyword to auto-generate a type for us, since usually the iterators are quite long types. And we just get the begin iterator, and then we check whether it's not equals to the end one. And then of course we need somehow to advance to the next element. And such an iterator is just an object which keeps some references on the container to which it belongs, and internally you can access the value the iterator holds, and e, comma, like this with the asterisk. You could of course, if it would be something more complex, use the arrow operator. That would be with Qt. If what the iterator returns depends on the data type. Just using the asterisk would work if you would have a vector, but if you have a map, then what it actually gives you is a pair which contains a first and the second element. The first element is the key, so the first one will be the string, so we would need to use here the first one would have a C string, and then we need to have a %s, and the second one, second is just the integer, and then let's maybe write here is equals or something, \n. Alright, so you can use these iterators like this to go through this element, through these lists, and it's usually the fastest way to go through them. With the vector, of course, you can just use the index, because the vector has a consecutive memory area, so it's easy to index the elements. If you would be using a list element, a list container, the list does not support the square bracket operator, so you cannot access a list by index, STL list. You only can access the first element, the last element, or you can work with the iterators along the list. And for many applications, being able to access the beginning, the end of the list, and that's it, and or go through it one by one is enough. You can also insert or remove elements from such lists at a given offset. Sorry, not offset, but at a given iterator value. So you have an iterator, and then you can say at this position insert something, or you can say remove something at that position. Yeah, but let's come quickly back to the homework. So final project. Create a class which can represent following types. One int 8, 16, 32, 64. So all the different integers. Segment and segment, signed and unsigned to float and double. 3 string and white string and white string, and it would be good if it could also represent arrays. So the idea is that it with an array of variants, that it really is then an array of variants of any type. So one can be an integer, the other can be a double, another can be again something else. So it's not like that you would want to implement something that just represents an array of integers, but we would want something that can represent just an array of arbitrary things. And 5 is also maps of variants. Maps of variants. And I think to make this simple, so to simplify things, you can use STL container class. STL containers like map, list, comma, vector, comma, etc. Okay. Good. And now to the optional things. Maybe wait, one more thing. Before we do the optional things, the variant must be able to convert between pairs when possible. For example, int to string or vice versa. So what we want is the ability that if you, for example, would have a variant which contains the letters representing the numbers 1, 2, 3, 4, and you want an integer, then you want the ability of for your variant to say, okay, I'm a string, I can use a conversion function like atoy or vetoy to convert to an integer, which was requested, and then it would return an integer value. So we want these conversions to be possible. We should maybe add some more details. Right here. Let's add one more type, which would be quite nice to have. We would want it to be able to represent a byte array, but only like in int 8. We don't need like an array of 16s or an array of floats. We just want a binary array just with binary data of whatever internal type. Okay, the variance must be collected for. Okay, the variance must have constructors for the relevant data types, and offer two x66 functions to cast. It's optional. What else do we want? Yes, we want so if you have variants which can be represented by numbers, if you make a plus operation, then it should return you a new variant with the result of the operation numerically. And if you would try to add, for example, if you would try to divide 10 through a string that says banana, then it should throw an exception. So if not if the pairs are not compatible, like 1, 2, 3 divided through bananas, then throwing exceptions, we had some exceptions with regard to C. We can take a look at throwing exceptions in more detail in the next lecture, but generally just write throw and then you write, for example, blah. You can throw in C, in C++, pretty much any object as an exception. So for example, the MFC class library has a explicit C exception type. So you could, for example, implement your own type of the sort exception. But if you just throw a character array that contains the arrow, that is just fine. And those can be caught in a similar way as exceptions can be caught in plain C. Just that you use the catch, you use try catch, and you don't use the underscores. You just use try catch instead of try except. And in the catch, you can specify which type of exception you want to catch. So you can have try catch and then the type. You can have you could throw an integer also, or you could just want to have an exception handle that catches everything. That will just catch everything, but then you don't know what to do with it because you just caught an exception of an arbitrary type. So you can just write unknown exception occurred. The usefulness of that is arguable, but here, if you know that it's an int, then you can throw exception from code 1 to 3 or something like that. Or if you have a string, then you can actually write %s, comma code %e, etc. So if as simple as it gets. You can take a look if you are interested in that during the next lecture. Let me know if you want to learn a bit more about C++ exception handling. But as said, the idea is that when you implement your class and you encounter an attempt to make a mathematical operation of something that makes no sense, then you just throw an exception which just says that incompatible type or something like that. That is easy enough. And now to the optional things. What would be nice would be if the variants would have a copy on write behavior, such that I think we have taken a look on that already with our string during the last lecture. Let me quickly check. But I think that was included. String. Take string. Yes, so we had our reference count, and we only copied it when it was really necessary. So we want optional to make the variant class use copy on mechanics. What would we? What else optional would we want? It probably would be nice if we could represent other types of arrays. So, or float double. Do we need arrays of strings? I think we don't do. I think we do not. That will be enough. What else would we want? If I remember correctly, we had something with regard to the strings here to represent them in UTF-8. Yes, so we could add this actually here as well. No, but that's not necessary. One more thing would be good. So serialize and deserialize means to right to so serialization and deserialization refers to the process of converting some non-trivial data structure to a simple representation which does not contain any absolute addresses that can be saved to a file that can be sent over network, it can be printed out on paper and scanned back in, and then from which you can then deserialize, so restore the original object. So in C, when you have your objects, you would usually have like memory addresses of other objects which they point to, and of course you cannot send this over network or save it to file, because to another program, even to the same program once it was started again, a memory address of the previous program will be completely meaningless. So the idea is that all the data within such a serialized representation refer to each other exclusively by offsets within that data stream, and not by memory addresses. Yeah, I think this is a good final project, because it helps you to use pretty much most of the useful functionalities of C++, and especially it teaches you how to, or rather it allows you to practice how to create your own data types, which in C is one of the more powerful abilities of the language. So many other languages do not allow you to create objects with this level of flexibility. You can use some built-in types, and then you can create objects which just have functions and members and properties, but creating an object which kind of behaves like a other object and creating own pointer types, etc., that is not something you can do in other languages normally. Okay, since we are almost out of time, I think we should be done for today. Are there any questions? No, you have time to the end of the month, and I think officially I need by 2 weeks after the end of the month have all your notes entered. So like the first week of the next month, if you need it, it's okay. The next 2 weeks, then I need to explain why I haven't given you a grade yet. So it would be good if you don't need more than so 1, 2, 3, 4, then 5 weeks from now. Ideally by the end of the month. 1 week is okay. 2 weeks means I need to explain to other people why you don't have your grade yet. So that complicates things for me, which is not desirable. Okay. So, any other questions? Yes, it should be in C++. You have operators only in C++. Okay, any other questions? Okay, if there are no more questions, then we'll see each other, I think, in 2 weeks, since the next week will be a holiday. Yeah, so see you. Bye bye.